I'm Jerry Capel, the CEO of the Library Foundation, and welcome you to the community room of the Civic Center because, as you can tell, if you've been to the front of the library in the last, year and a half, a little bit of construction going on. And so they have limited the number of people in the Friends Room to 40. Well, there's more than 40 here tonight, so it's not right. It's been Spotlight on Science has been really for second 2.5 years now that we've had it. It's been one of the most popular programs we have, and it's due to the people that are involved in the committee. You saw their names previously that worked very hard. And I want to introduce to you a board member of the Library Foundation of Newport Beach and the co-chair of the Spotlight on Science Committee, Randy Heisen.
Okay.
These men, I thought that.
Let's see here. If I get this one.
Yeah.
Want to make sure we get the.
So thank you for your patience tonight. There's a lot of people coming in here, and we're kind of heavily subscribed. It's just great to see everybody here and give them time to come out of the garage. So I have one slide to show. I'm going to speak for a minute to introduce our speaker tonight. Welcome to the Spotlight on Science. This is our third season, actually. Really, on behalf of the committee, we'd like to welcome you all because this is one of the many outstanding programs, and just one of them that the Library Foundation brings us together to hear from the world's leading authors, artists, journalists, doctors, and scientists on topics of interest, relevance, and importance to our community. The objective of Spotlight is to transport you into the worlds of scientific research in an understandable and accessible way, and to describe the importance and inevitable impact of these endeavors on our lives and our communities. As a reminder, we'll be covering topics ranging from the infinitesimal to the infinite, exploring the sciences of biology, chemistry, physics, optics, neuroscience, electronics, the environment, and cosmology. Our 5 broad topical categories include the human body, our planet, energy and transportation, the worlds beyond Earth, and emerging technologies, which is the category for tonight. And we'll be visiting these on a rotating basis each season. You can find all of our prior program videos archived on the website as well. Also, please calendar our upcoming sessions for next spring on the future of small satellites, Dr. Charles Norton from JPL and Caltech, and followed by our grand finale this year on matter, antimatter, and the evolution of the universe, with a talk from Nobel Prize winner Barry Barish from Caltech. So some good stuff coming along. Jerry mentioned the foundation. I wanted to just reinforce this happens because of the work we do. And our motto is to support discovery and connection beyond books. So this is where you can learn and connect with your fellow neighbors and people in the community. And it's really through our programs and the embellishments that we bring to the library that we get this. We have the Witty series and Library Live, which is focused on authors, journalists, and literary figures to spark community conversations. We have the financial literacy workshops, which provide up-to-date information on managing your money and your estate, while Medicine in Our Backyard highlights the latest in health and medical advances in association with our partners at UCI Health. And finally, we have a wonderful book discussion group, probably one of the largest in the state, as I've heard about it. It inspires people to open their minds and hearts through reading inspiring and entertaining books throughout the year. But we also go beyond the programs, and we fund some amazing embellishments in the program, including Media Lab, where we're going to add a podcast studio, self-checkout computers, and tech toys for kids, the Wayfinder, and a branch of digital resources. And just because we can't do this without you, I'm making a pitch for you to join or renew your membership in the foundation, because it really benefits the entire community. Jerry always reminds me that we have somewhere close to 3 million contacts with the community through the library, through all of the engagements through the year. We rank only second to the beaches and the harbor in a public community resource for our community. So really, this is all of us. We're coming together to do this. So, and if you've attended any of the programs, you saw the beautiful vista of the new Whitty Hall that's being built. And there's a reason we're in this room tonight. We're shouldering 50% of the cost of a $24 million building that will belong to the city. Many people in the audience that I can see them have spent a lot of time bringing that to fruition, raising the money, getting it through the city council. They voted right across here after a lot of struggles to approve this, and to have a great resource for the community. So please, we are still in the last vestiges of our fundraising campaign. Please join us in making that vision a reality. I guess the last thing is you can check in the Jerry website if you want to join. So let me talk about tonight. This happens to be one of the most popular programs we've had, and it was originally entitled "What You Should Expect to See from Quantum Computing and When Will It Happen." And talking with the speaker, Doug, we sort of changed the phrase into how quantum computing will reshape our world and when. Okay, because it's coming, and you're going to learn about that tonight. You may not realize that some aspects of quantum have already reshaped our world. In fact, the now ubiquitous transistor that powers all of our computers and all our electronic cell phones, I think there's actually something like 12 billion transistors in this thing here. It's actually a quantum device, and it was invented in the mid-40s, but it was a direct outcome of the science that began 100 years ago. And you're going to hear that story. So these are the stories that we like to talk about here, because it takes the scientific research and translates it into global impact. So quantum is just getting started. You're going to hear that quantum computing, along with its cohorts, quantum sensors and quantum networks, which we don't have time to get into tonight, might be considered quantum 2.0. And not only is the science more than a bit unusual, so is the way the scientific research is being done. It's a simultaneous acceleration of investments into both our academic and our government institutions, all the while being accompanied by our large public corporations and a massive venture capital effort. So this is really a global race to bring quantum into reality. Its fantastical boost of publicity and funding is due to both the potential commercial and geopolitical payouts. We had a conversation earlier this evening about China and what they're doing. So we have superpowers, tech powerhouses, VCs alike, all jockeying for supremacy in this exciting new area. Indeed, quantum has been in the news a lot over the past 10 years, and will also play an important role. I just made one slide to show how much is going on here. So this starts about 10 years ago at Time Magazine. I just looked up some of the covers of the technical journals as well as the business journals coming from Time Magazine, bookending a 10-year span. And then just a few months ago, the quantum era has begun. This is this year. And just in the last few hours, Doug has posted some new news that we're reporting to Congress on what's going on in quantum computing. So we really have a lot to talk about. We're very excited to bring tonight's speaker, Doug Finke, who is a leading authority in not only how quantum computing works, but where the research stands, who's betting on which architecture on the competitive playing field, which applications are most likely to emerge in the near term, and when we might see this impact in our daily lives. Doug's work to analyze, track, and forecast these outcomes of all the research and ensuing commercialization, to me, rivals the complexity of the science itself. But first, I'd like to introduce one of my Spotlight Committee colleagues and a long-term friend from the laser and optics industry, Don Silberman, who is responsible for recruiting tonight's speaker. Don himself is an accomplished optics industry professional turned science educator, now working mostly with schools to develop interest in STEM in optics, and runs the Quantum Optics Institute of Southern California. Don holds a BS in engineering physics from the University of Arizona and a master's in technology management from Pepperdine, and has been working in astronomy and laser-based applications for over 40 years, some of those with me. And in fact, it's through a connection that he made at our inaugural Spotlight on Science series that led him to the connection to Doug. So Doug and Don both share a deep passion for and a practice in science education. So please welcome Don, who will do the honors of introducing our friend and Doug. Thank you.
Thank you all very much. It's quite an honor for me to be able to introduce Doug. And what I want to tell you, though, right now is that over 100 years ago, the world's top scientists were able to we're trying to answer questions about the fundamental natures of the universe, such as questions about atomic spectra, radiation, the stability of electrons in orbit around the nucleus, and radiation. What is that? So these and other mysteries were not included in Newtonian physics, which basically govern all our macro type of experiences in this world. In December of 2019, the U.S. government passed the National Quantum Initiative to help fund and encourage U.S. companies, universities, and national laboratories to research the use of several quantum phenomena that had not yet been much used in our modern civilization. Doug will be telling us about those in just a few minutes. Many other countries passed similar laws or initiatives to do the same in their countries, and last year, UNESCO designated 2025 as the International Year of Quantum Science and Technology. In June 2019, the Optical Society of Southern California had 2 speakers on the topic of quantum computing. Doug attended that meeting, and we became friends after that. Doug studied computer science at the University of Illinois, Urbana-Champaign, and received his master's degree in management from the Massachusetts Institute of Technology. He founded Quantum Computing Report website in 2015 after many years as an executive in the semiconductor industry with companies like IBM, Intel, and Western Digital. In December of 2022, he joined with Fact, Faith, Insight, and Inference Advisors and formed Global Quantum Intelligence to provide trusted data, insights, analysis, and advice to vendors, users, investors, and governments to help guide their business, policy, and strategic decisions in the quantum tech domain. In 1956, Isaac Asimov wrote a short story called The Last Question. It's a science fiction story that begins in the year 2061, when 2 people working with the multivac, a self-adjusting and self-correcting supercomputer, posed the question about the fate and nature of the universe, akin to those posed by Dr. Bullock, who was our inaugural speaker here from UC Irvine, and many other astronomers. Could quantum computers become a real version of a multivac? Well, Doug will tell us the story of quantum mechanics and its evolution into computing, along with the players, opportunities, and challenges ahead to help us answer these questions as humanity discovers the uses of quantum computers to help us reach our human potential. Please join me in welcoming Doug Finke to the Newport Beach Public Library Spotlight on Science.
Yeah. And it,
There we go.
we're off.
Okay. Well, thanks for the kind introductions. I was asked, how did I get into quantum in the first place? I call myself jokingly a refugee from classical computing. I started my career at IBM, designing mainframe computers. I worked at Intel, Western Digital, did a whole bunch of Silicon Valley type startups. But there was one thread that went through many of my positions, which was always involving high performance computing. So I always was interested in it. And as I started looking through it about 10 years ago, I started looking, I saw on the web, quantum computing. It was a new paradigm, new way of building a computer that could achieve high performance computing. And no one was talking about it. There was no analysts talking about it. The only thing you would see are, very deep technical papers that people would publish in the scientific journals. But I felt there was a need for someone to talk about it, what the market potential is, and talk about it a little bit more from a business standpoint. And so I decided to be the first one. And I was used to people doing that type of thing in the classical computing business. There's tons of analysts who talk about high performance computing and semiconductors and disk drives, all those things. But no one was doing it by quantum, so I decided to be the first one. It started slow, but basically the quantum industry has really grown much faster than I anticipated 10 years ago. It's grown exponentially, and it's really a fascinating area, and I'll talk about that. My organization has also grown. I've partnered with a couple of people. We now have an organization of 16 people. We're a leading business intelligence company for the quantum industry. We only do quantum, and we have people, myself in California, we have people in Florida, Washington, D.C., London, the Middle East, India, and everywhere. So we do a lot of work with governments. We do a lot of work with investors, vendors, as well as things like due diligence reports and other reports. Okay, so with that, I'm going to start and talk about the basic principles of quantum computing. And my goal is to give you an intuitive understanding or some understanding of what it is and why it works. As Don had mentioned, there was a lot of work being done 100 years ago investigating various phenomena that they could not explain with Newtonian mechanics. And there were a bunch of conferences, various theories came about, and probably one of the more famous ones was the Solvay conference, which happened in 1927. It turned out people like Einstein and Bohr and Madame Curie and a whole bunch of other people, very, very famous physicists, attended that. And they really started coming up with some new principles of quantum mechanics 2.0 that people had not thought about. Of course, the transistors came out of that. Interestingly enough, 17 out of the 29 attendees at that conference won Nobel Prizes, or were going to win Nobel Prizes. So it's a very important conference, and it really led to where we are today. One of the things to understand, though, about quantum, and this is from Richard Feynman, who was a very famous physicist at Caltech for many years, it's not intuitive. And he says, look, if you think you understand it, you really don't. But for today, there are 4 specific principles we call Quantum 2.0 that came out of some of those studies 100 years ago. And the important thing is those principles were not leveraged in classical computing. Classical computing used other things, transistors and Ohm's law and things like that, Boolean logic, things like that. But for almost 70 years, people didn't really know how they could leverage these principles. They knew it existed, but they couldn't leverage it. And I'm going to walk through that right now. So the first one is called tunneling. It is possible, if you have an electron and a very, very thin barrier, thin wall, for that electron to go right through it and go to the other side. That's called tunneling. It's part of Heisenberg's uncertainty principle. Now, I can't walk through that wall, but an electron can. And the first place where that was used was really discovered or really implemented in the 1970s in something called flash memory, which is memory. And today, that is used in cell phones. I have, I think it's 12 gigabytes of flash memory in this, and that is all based on the tunneling principle. But tunneling is also used in another type of quantum computer called a quantum annealer that allows you to tunnel through an energy barrier to help you find a solution to a problem. The other thing that came out of this conference was this concept of superposition. I think we're all familiar with digital logic. It's either a 0 or 1, but it is possible at the microscopic level within atoms and those types of things for a particle or something to be in a state is a superposition of both the 1 and 0 state at the same time. And again, that's certainly not intuitive, but I'll talk a little bit more about that. But that is one of the keys to getting you the power of a quantum computer that you can't get in a classical computer. Another thing is interference. You know, we have interference in the physical world, and that's where you have two waves that will come together, and if they're both in phase, they will highlight each other. It pointed out to me that here in Newport Beach we have the wedge, and you have at the beach, you go to the wedge. If two waves come together, you have these monstrous waves. But it also happens in electronics. You can sort of see the waving lines at the bottom there, where the red and the blue and the green guys, when they come together, the red is like a combination of the two. But it's also a very famous experiment is called the dual slit experiment. Light, photons can behave both as photon, but both as particles and as a wave. And the interesting experiment in the upper left corner there is the fact that you can have, it's called dual slits, where, Troy Don's little thing here. Okay, it won't work. Okay. Where you shine a light through two slits, and it comes up with an interference pattern, as you show in that gray and white. And that sort of highlights the fact that they're waves, and sometimes the waves come together. That's called constructive interference. And sometimes the waves are in opposite of each other. That's called destructive interference. And that is actually a technique that's used in order to get the quantum computer to provide you with the right answer. And the last one, which is really not intuitive, and in fact, Albert Einstein called it spooky action at a distance, is called entanglement. You are able to take two particles, and the particles are called qubits, which I'll talk more about that in a second. You can entangle them like they're like twin brothers. And then once you do that, you can separate them out, and they will still react. If you do something on one qubit, it'll happen to the other qubit instantaneously. And it's very, very strange. People didn't believe it for a long, long time, but you can do it. It is there. And that is a key principle that makes quantum computers as powerful as they are. So, moving on, there's this thing called qubits. I think we're all familiar with bits. Bits are the fundamental information thing that carries information in classical computing. It's either 1 or 0, and you can see in the light switch here how that works. Qubits can store information also, but they can contain this entanglement and this superposition. And the way the qubits are denoted is with this globe here. It's called a Bloch sphere, where you can represent the stage of the qubit in that sphere. The North Pole is equivalent to a 0, a classical bit. The South Pole is equivalent to a 1. But the equator, I said you can have 0 and 1 at the same time. That's what the equator would represent. That would be sort of a mixture, a probabilistic mixture, 50-50 of 0 and 1. And then you could also have different types of mixture. You could have a 25-75 mixture. So 25-75 might be in somewhere in the northern hemisphere. So qubits are represented by the globe there. And one of the ways to program a quantum computer is by implementing what are called quantum gates that move the state of the qubit from one position of the globe to the other. And you can see that on the bottom right of this, where a qubit is just moving around. Now, qubits also have some other issues. First of all, they're very fragile. Qubits can unintentionally, they can collapse to like a 0 or a 1 state. If you wanted them to stay at the superposition state or the equator, any slight environmental disturbance will make it go to a different state, probably the 0 or the 1 state, and that's bad. Because all the magic happens when the qubits are in that superposition state. So as you'll see, the quantum engineers, the people working on these systems, go to a lot of pains to try to prevent that as much as possible. And that is actually the biggest issue right now we have in quantum computers. That's why they haven't developed quite as fast. And to put some numbers around it, the classical computers, the cell phones we use, they're very, very reliable. If you do an operation through a transistor on a classical gate, you can do it 1 million times or 1 billion times. You can do it for 1 million years, and it will always give you the right answer. And that's called the error rate. And you can see the 0.00000, etc. 1. That's how reliable the classical bits are. But if you look at the bullet right beneath it, a qubit, that has an error rate of 0.1%. And that means that if every time you do 1,000 operations on a qubit, one of those operations is going to be bad. And that's not good, because to do real work, as I'll show you in an upcoming slide, you're going to need billions and billions, maybe trillions of operations in order to do that. So there needs to be a lot of work done, and there is a lot of work. That's probably the hottest area of research right now. It's something called quantum error correction. I won't go into details. It is a little bit complicated, but that's one of the things that a lot of the researchers at IBM and Google and the others are working on. Okay, so I talked about the qubits. Well, how do you actually build these things? And you can separate that into two classifications. There are, what we call the natural qubits. These are things like atoms or ions. Someone once said, these are things that God made. God makes the atoms. And the thing about atoms is they're all identical. That if you take a silicon atom and another silicon atom, they're very identical, and that helps you in some ways. It helps the error rate, but you can build it in different types. A trapped ion is basically an atom with one of the electrons missing, so it has a charge. A neutral atom has the balance between the electrons and the protons, so it's no charge. You can have photonics. We talked about, we showed the photonics earlier. People are sending chips that will send photons over a little chip. And I'll talk about that. And you can have what are called diamond vacancies, where you can take a diamond, which is and put in one of the spots where, diamond is all carbon, carbon hooked together. But in one of the spots, you substitute a carbon with a nitrogen. So there are companies working on that. Of course, their motto is diamonds are a quantum engineer's best friend. So there are one of the things that's really exciting about this industry is that a lot of different companies, and they're all trying these different approaches. So, I see that as very healthy, because we don't really know right now which one's going to win out. And they all have their pluses and minuses. Now, the second classification are what's called synthetic qubits. These are things that are actually, you have to manufacture with the thing. A lot of these are manufactured in a semiconductor wafer fab using the various deposition machines and lithography and all those types of things. The one at the top, superconducting circuits is built using semiconductor technology, where the patterns are super cooled to almost absolute zero. That was actually the technology that won the Nobel Prize a few weeks back. John Martinez and Michel Diberet and one other guy, they won a Nobel Prize for demonstrating that you could build qubits that were at larger than the atom scale, at the macro scale. But there are other things, silicon qubits, which is very, very similar to semiconductor technology. And then Microsoft is working on something called topological qubits, which have some potential advantages for the reliability problem that I talked about, as well as speed and how small you could make it. So, give you a couple of pictures of various implementations of quantum computing. This is some of IBM's systems. Their latest system that they're installing worldwide now is called the IBM Quantum System 2. That has 156 qubits in it. When I started the quantum computing report, they had just come out with a 5 qubit system. So in 10 years, they've gone up by a factor of 30. It is built with a chip. You can see the chip held in the hand there. And that chip is held in a dilution refrigerator, which I'll show in more detail in the next slide. The nickname for the dilution refrigerator, by the way, is called the chandelier, because it sort of looks like a chandelier, and people just started using it. And one of the things we track is IBM's roadmap. I was actually at IBM's conference in Atlanta last week, a week ago this week. And they unveiled their roadmap where they're going to take many of those systems, similar to the System 2, and networking them all together. That's what's shown in the bottom right of that chart. But let me, go a little bit deeper into this dilution refrigerator. So the purpose of the dilution refrigerator is to cool these things down. I said that heat is an enemy of the qubit, and that's because a qubit is a little bit unstable, and then some high temperature comes in and it'll destabilize it. So they create this environment where it's very, very low temperature, 15 millikelvin. They put it in a vacuum. They put magnetic shields around it. You can see that in the right picture. And they try to isolate it from the external environment as much as they possibly can. And that helps them improve the reliability of the qubits. And just to give you some sense of how cold that is, people say that the 15 millikelvins is the coldest spot in the universe, because it's 1,000 times colder than outer space. Outer space is like 2 or 3 Kelvin, and we're talking 15 millikelvin there. Another system, this is actually one of the very first that was put on the market, is a company called D-Wave. D-Wave is based in Vancouver. They have an office in Palo Alto. And this is what a packaging system looks like. It is also built with chips, as you see on the right. And that uses a technique called quantum annealing. It's a different approach than some of the other ones, which are called gate-based systems. But it takes advantage of that tunneling that I talked about. It turns out, by the way, that there is a D-Wave system not too far away. USC has one in Marina Del Rey, and they've had it installed for many, many years, 8 or 9 years now, and it's gone through about 4 upgrades. I think when I first started, the D-Wave system at Marina Del Rey was 500 qubits. Now the latest thing has something like 5,000 qubits. And, I said that these are built in what are called fabrication foundries or fabs, is the nickname. And it uses many of the same production equipment as semiconductors. And that's one of the things the industry is trying to do. You want to leverage as much as you possibly can the 70 years of development of semiconductor manufacturing in order to build these things. And this is an example of the D-Wave chip is built with a company called Skywater Technology in Minnesota. And those are some of the machines that are used. Now, there's another company. This is a company that's using photonics. And that's different. It is different. They do use semiconductor techniques, but rather than having physical qubits or atoms or ions, you actually shoot out photons. And the photons will go and they will interact with each other, and then you will detect them, and that's how it works. And you can see the various elements of the quantum. They have chips. They put the chips into blades. They put the into packages. They put them in the cabinets. I think the thing that's sort of unique about Skywater, I have some about PsiQuantum. Their goal is to have a 1 million qubit system roughly by 2027, 2028. But it is a very, very large system. They've signed deals with Australia, Brisbane, Australia, the government of Australia, and in Chicago, the state of Illinois, to build giant facilities. I think it was 100,000 square feet, costing roughly about $1 billion each. And these facilities are going to have 300, 400 cabinets. But their goal is to be the very, very first one to be able to produce a very, very powerful quantum computer. Some might call it a brute force type of approach, because I don't think people will continue spending $1 billion for a quantum computer. But for the very first one, maybe they will. So that's certainly a company to watch, and of course we've been reporting on them for some time. The other thing to understand about quantum is that quantums will not be used isolated. Another area of research, and it's actually something that was discussed at IBM when I was there last week, is how do you put together quantum computers and classical computers together so that they work together? There's a lot of synergy between the two. There's a lot of algorithms where you might do one part of the algorithm classically and the other part of the algorithm quantumly. So there's a lot of work to be able to have the two work together. One announcement maybe you saw, there's a company called NVIDIA. And NVIDIA just announced something, a technology called NVLink, which creates a link between the classical computer and the quantum computer that runs very, very fast, because speed is always important. And they announced just last week, and then just on Monday, they announced that they now have something like 30 different companies, both quantum providers as well as what are called HPC centers. HPC stands for high performance computing, to have the two work together. So that's going to be a very important thing, that you want to have high performance classical computers and high performance quantum computers working together to get the best possible result. Okay, so I've talked a little bit about the technology. I'm going to talk about how people are going to use this now. So I talked about entanglement. I talked about interference. I talked about superposition. And this is a chart on the right that shows one of the reasons why qubits are better than bits. And the difference is really simple. In a classical register, let's say you have two classical bits, it can be put in the states of 0, 0, 0, 1, 1, 0, 1, 1, but it can only have one of those at a time. So that's where the number 4 comes. 2 bits can hold 4. A qubit, because of the superposition and entanglement, it can hold those same 4 things, but can also hold 2 at a time. It can hold 3 at a time, or it can even hold all 4 of those states at a time. So that creates more opportunities for you to store different states and allows you to have more things in that. And that's one of the reasons that people can take advantage of quantum computing. And or to put it another way, you know, people are talking about these very large data centers that hog a lot of power. You know, people are talking about classical data centers that may have 20,000 or 30,000 NVIDIA GPUs. If you want to double the size of that data center, you have to double its size. You have to add another 20 or 30,000 GPUs. And that's why, you know, there's sort of a speculating war going on. Who could spend more money? Is it going to be Microsoft, or is it going to be Google, or is it going to be Anthropic? You know, they're all almost competing to say who can build the biggest data center. But it's sort of another brute force way of achieving performance. In a quantum system, you double the performance by adding 1 qubit. So you go from 100 qubits to 101 qubits. So there is greater ability to expand performance and a much more efficient way of doing that. So let's talk about why quantum has any potential. And I want to start with sort of a basic problem that is taught in almost all computer science courses. It's relatively simple. It's called the traveling salesman problem. So you have a guy, he's given a bag of products to sell, and he's given a list of cities that he has to visit. And maybe it's 3 cities or 5 cities, and he has to drive. They won't give him they won't let him fly. So he wants to come up with a way of using the least mileage. You know, I want to go from Newport Beach to Los Angeles to San Diego to Seattle to Portland to Boise. And he has to figure out what is the right order that he has to travel to go through. Now, that's a simple problem. If it's only 3 or 5, he can do it in his head. If it's more 5 or 10 or, you know, maybe 15, there's actually computer programs, classical computer programs that will solve that for him. But this is a problem where as you start adding cities, the number of possibilities grows by what's called a factorial process. If you give him a list of 100 cities and have him try to figure out what is the most efficient way that he could travel to all those 100 cities, the number of possibilities is something like 10 to the 50th or 10 to the 75th. Huge. And it's not only beyond what someone can do in their head, it's beyond what even a computer, even these large data centers I was just talking about before, they can't figure it out at all. So it turns out there are many, many problems like that where even these very, very large classical computing centers can't solve the problem. And that's really where quantum fits in. So, you know, the way to visualize that is with this graph here. So you can always characterize a problem by what I call the relative problem complexity. It could be the number of cities. It could be the number of atoms in a molecule. It could be even just a list, what's called an unordered list that you have to search through to find the right thing. And the vertical axis describes the length of time or the number of operations you would have to do that. Now, you know, the interesting thing is that if the number of operations, the complexity of the problem is small, classical computing will beat out quantum every time, because the fundamental operation of of a quantum computer is actually much slower than the fundamental operation time of a classical computer. But the reason quantum wins is as you increase the complexity, as you go to more and more and more things, the classical computing time will rise, and it may rise what we're called exponentially or factorially. In other words, the slope of that, the line there, I have what the black line there, is really, really high slope. And the thing about the quantum is the quantum solution can it is a much, much lower slope. So at high complexities, quantum wins. And to give you a very specific example, take a problem, and we do this ourselves, and you have a list of stuff. Maybe it's files on your hard drive, and you're trying to search for a specific file, and it's what's called an unordered list. And the way a computer would do it is, okay, check one, is it the one I'm looking for? No. Check two, is the one I'm looking for? No. 3, 4, 5. And if it's like 100 things, if you get real lucky, you'll hit it on number 1. If you're very unlucky, you'll hit it on number 100. The average, though, will be about 50, if you think about that. In quantum, there's this algorithm. It's called Grover's algorithm. That will do it in the square root of the number. So Grover's algorithm could do that same thing in 10. The square root of 100 is 10. So that's why quantum wins, is, again, large complexity, that the slope of this line, it does not grow as many operations as the classical. So I show different type of computers there. One's called NISQ, one's called fault tolerance. I won't go into the details of those, but those are different types of quantum computers. Both are designed to help combat some of those areas I talked about. So where are we today? So, X marks the spot. This chart here is something actually provided by DARPA, the Defense Advanced Research Projects Agency, for something. And those dots, I'm not going to explain all those dots, towards the upper right, but those are estimates of the number of qubits that are required, as well as the number of operations that are required. So, I said, X is currently about 100 to 200. You can see some dots that are in the upper right-hand corner that are going to take, it's hard to read here, 1 million qubits. And these are actually what are called logical qubits. And the number of operations required are 10 to the 21, which is, quadrillion or quintillion or some huge number. And if you remember my earlier slide, I said the current error rate is 0.1%. That means 1 out of every 1,000 will fail, and that's where this 10 to the 3, the same as the 10 to the 3 I have in this chart. So in order for quantum computers to solve some of these problems that are represented by those dots there, you're going to, the industry is going to need to expand the number of qubits by something like 4 orders of magnitude. And they're going to need to increase the reliability by, about 7 or 8 orders of magnitude. So there's a lot of ways to go, but the important thing to understand is that all the efforts in the quantum industry, all the hardware providers are working. Actually, there's 2 efforts going on. The hardware providers are working to try to move that X farther to the right, towards the right corner. And the software guys are trying to come up with more efficient algorithms to move some of those dots, which represent applications, and move them down and to the left, so they take fewer numbers of qubits and fewer operations. So, that's why there's a lot of work. A lot of people are working on these problems. So, talking about applications, there are a lot of applications for quantum computing, and let me go through some of them. Probably the one that's going to impact society the most is what I call computational chemistry. Drug discovery. All the big pharma companies are working to try to figure out ways to develop new drugs much faster and more efficiently. To develop a new drug these days costs over $1 billion in over 10 years, and it's very, very expensive. The goal is to try to reduce that perhaps by an order of magnitude. And the reason that drug companies think they might be able to do that is, previously, a lot of drugs are discovered what I call empirically. They had maybe 10,000 test tubes or something like that, and they would try each one. If you could simulate what's happening, let's say the drug with the virus, and simulate it inside the computer, you could do it a lot faster, and you wouldn't have to spend money for all the test tubes and all the other apparatus to empirically test it. So there's a lot of effort being put on now. I would also point out that, of course, drug discovery is just one aspect of computational chemistry. Battery chemistry, as we all know, that electric vehicles are hot, and the battery chemistry, the companies like Mercedes and BMW and Ford are putting together teams to figure out, well, is it lithium ion? Is it lithium sodium? Is it, sodium air? All those types of things. And by simulating it in the computer, they want to come up with batteries and have longer lifetime, longer charge, and can charge faster. But of course, as Madonna says, we live in a material world. Materials design, new types of steel, new types of things. How do you put alloys together? That's another area, as well as carbon sequestration, catalyst, and those types of things. A lot of applications for computational chemistry. There's quantum machine learning. I said earlier that AI, classical computing and quantum are working close together. Well, there's a lot of work being done on AI and quantum working together too. And it's two types. One is taking advantage of AI to help improve your quantum. Engineers now are using AI techniques to figure out how to design better quantum computers. They're figuring out. Oh, I'm sorry. I have the titles mixed up. The top where it says AI for quantums should be quantum for AI, and the second one where it says quantum for AI should be AI for quantum. But anyway. But the things like, I had a quantum error here, so. But what are called error mitigation, algorithm design, calibrations, those types of things. Engineers now, quantum engineers are using AI to help them out there. And then, of course, quantum can help AI. You can accelerate things like training. Quantum does linear algebra very, very well. So any problem that you can solve with linear algebra, it can do that. Natural language processing, the company has developed some natural language processing and what are called clustering algorithms. Another area that could have a big potential payoff, and the big financial companies like JP Morgan, Goldman Sachs, and others, they have teams working on quantum. There are a lot of mathematical problems in finance that people use computers for. There's things called Monte Carlo analysis. There's portfolio analysis. The chart there on the right is what's called currency arbitrage. And it turns out that the combinations of different things that you can put together, a portfolio analysis, and what that is you may have a market basket of 1,000 different stocks that you can buy, and you want to pick a combination of stocks that give you the best yield at the lowest amount of risk. That is actually a pretty hard problem. A lot of times people use what are called Monte Carlo analysis. Quantum can help that. And the reason the financial companies are so interested in this is if they're running $1 billion portfolio and they can improve the yield on that portfolio by 100 basis points, and that's 0.1% without increasing any risk, that's a lot of money. It's $10 million. So really small improvements can mean a lot, particularly in the financial industry. So there's a lot of work being done there. So someone asked me earlier, what are the bad parts of quantum? And quantum, one of the things that was discovered, and this really helps set the industry off, was quantum can be used potentially in the future for code breaking. So all the transactions we do on the internet today through the web are done with encryption. And the encryption algorithm that we use was actually developed in the 1970s. It's something called RSA. And it was based on this problem of what was called a one-way mathematical function. And specifically, the problem was factoring a large number. You can see in the thing on the left, it's easy to take two numbers, multiply them together, and get the result. Classical computers can do that in microseconds. But doing the reverse is actually very hard. To take a very, very large number and figure out what are the two prime numbers that have been put together to do that can take millions and millions of years. And that's why this RSA algorithm works. So the whole internet, as well as other things, have completely migrated to this. And in 1995, a scientist by the name of Peter Shor, figured out, he says, if I had a quantum computer and I can take advantage of entanglement and interference and all these other things, I can develop a quantum program that can do that in a realistic number of times. And he published a paper, and at first, people didn't believe it, but, the other people looked at it, and it actually is true. You can create, you can use a quantum computer, and that was in 1995, and that's really what kicked off a lot of the funding. The U.S. government said, oh, okay, we got to do this. And there's a lot of things happening. Now, you still require, 1 million qubits to do it, and you still require a large things. It is one of those dots that was in the upper right-hand corner of that chart that I showed earlier. But we do believe that, let's say, between 5 and 10 years from now, that those quantum computers will become available. And there's a lot of worry, of course, that the Chinese might get something like that. So there is a big effort to come up with alternate ways of encryption. RSA over the next several years will be replaced by a different algorithm that was approved by NIST. That's the National Institute of Standards and Technology, that cannot be broken by quantum. But this is a very important thing. So this is the only area, someone asked me, where quantum can be used for evil, and this would be the one area. Everything else that I showed you before was positive. Logistics and scheduling is another one. Think of a Federal Express drivers, sort of like a variant of that traveling salesman problem I showed. Was actually put into production at the Port of Los Angeles, where, if you've ever been there, they have the ships coming in, they have the cranes that offload the cargo things, and then trucks come in and you load it on, and someone came up with an algorithm and a process to optimize that to do better, and that's some very good results. Okay, again, briefly done through the quantum ecosystem and the quantum systems. So one of the things that we look at in our company is this thing on the left called a stack. So quantum is not just a single chip. You need a chip, you need to put it in a box, you need to have that dilution refrigerator there, you need a lot of electronics to control the qubits, you need algorithms, you need frameworks, you need development kits, and of course at the very top is users. So there's a lot of different things that need to happen to create a quantum computer, and all these things have to work together. So when we look at the ecosystem, what we see is that some companies will decide to be what I call full stack. IBM, for example, they will do everything. Microsoft is doing everything. Google's trying to do everything. And there are other companies that are specialists. Some people just specialize at the chip level, and then you see them more on the right. Some people, we call it mid-stack, and these are people who develop either control electronics or lasers that help you control the qubits to do those gates that I was talking about earlier. Or you have people participating at the top. So we have a full list of people. I won't name everybody on this list, but it's a lot of companies. There's roughly 300, 400 companies working in quantum. Many of them, the ones on the left, of course, are what we call the tech majors, but there's a lot of startups in there that are working. NVIDIA is an interesting company. They don't do the quantum hardware itself. They really specialize in this area called the MinStack. The government's quite active, actually. Just as a press release that came out a couple weeks ago from the Department of Energy, there's been ongoing U.S. programs for quantum. This was an award of $625 million for spread over 5 Department of Energy research sites. Some of them you may have heard, like the Lawrence Berkeley National Lab or Brookhaven National Lab, and some of the others. So the government itself is not only providing some money, they're providing researchers. A lot of national initiatives. We'll go through all this, but they're there. Okay. And there's a lot of international alliances. Companies are getting together. Countries are getting together. And they're working with friendly partners. The U.S. is working with China, with the UK and Australia and those types of things. Quick forecast: the worldwide economy a few years ago was $91 trillion. Cool. And here's the segments of it. And what we've done. Let's go back here. Quantum can be used, various aspects of quantum can be used in every single one. Some of them might be quantum computing, some of it might be for encryption, some of it might be for quantum sensing, but quantum will have an impact on every aspect of society. One of the things we do, we have a market forecast, a very detailed market forecast. I'm going to give a big talk in Silicon Valley about it next month. But we see that by the year 2050, quantum will create $1 trillion of value. Now, what's interesting though is of that value, we split it into 2 pieces. There's the revenue that the quantum providers themselves, people like the IBMs and the other companies will get from people purchasing quantum computers or the software. And then there's the value that the end users will get. People like the pharma companies that will perhaps develop a new drug and get billions of dollars of sales. And the interesting thing out of this chart is the split is like 20-80. The end users are going to take roughly about 80% of that value, and the providers will get 20%. But don't cry for them. That's still almost $300 billion. That's still done pretty well. Governments have been funding a lot. China in particular, the best number we have is $16 billion. Europe, that big circle in the middle, is about $9.6 billion. The U.S. has put in roughly about $5.3 billion. Of course, this is government only. The good news about the U.S. is that there's a lot more money coming in from venture capital, as well as the private, the public markets, and that is helping. From total funding from a provider standpoint, that's helping to offset the balance. But every country wants to be the leader in quantum, so they're all investing a lot of money. It's very political, a lot of geopolitics involved. This is venture capital investments. Venture capital is growing quite rapidly. These are the various stages that people are at. The one thing I would point out is the venture capital investments most of the money, is the biggest chunk of money is going into the cloud hardware. And the reason basically is simple. Hardware costs a lot of money. If you need one of those dilution refrigerators I mentioned, it alone costs $500,000. So you have to buy those, and you have to buy lasers and all that type of stuff. Those are expensive. If you're a software company, you just have a bunch of guys sitting at a PC, that's cheap. Yeah. And again, here's another look at the public markets. I think that the big trend I want to highlight is the fact that recently there have been a lot of companies that have gone public with what are called SPAC mergers, and they've gotten some amount of money, and then they've done a lot of follow-on financing with what are called at-the-market type of financing. So the good news is some of these companies have hundreds of millions of dollars of cash right now available, even though their revenues may only be $10-20 million, and they're losing a lot of money. They're losing could lose tens of millions or hundreds of millions of dollars in terms of operating or in terms of losses, but the market is getting the money. So we'll see how long that lasts. So just a quick conclusion. The quantum is coming. The thing that will make it really, really happen is the fact that the hardware guys are working really, really hard. The software guys are working really, really hard. They're both getting better, and very shortly they'll start meeting in the middle there. And we'll see what I call quantum production advantage, where people will be actually using this thing for real things. We are tracking a number of use cases. There's a handful right now, maybe 2 or 3, where people are using this on a production basis. But we're going to see a lot more over the next few years when that comes along. And, the thing that I want to tell people, there's this thing called Amari's Law. It's quoted by Bill Gates, saying that in a new technology, people overestimate its potential. And over the long term, they underestimate its potential. I certainly think that will happen in this collective. So I do have one last thing to show you, which is a demo. So one of the things we're always concerned about in quantum is educating a workforce. You have a lot of young people who are interested in quantum, and you need to find ways of doing this. So I ran into a startup company. Startup company is called Kohler. It's based in Maryland, and they've developed these little balls here. You just get them out here. The ball is called a qubit, and this represents a qubit. Remember I showed you the little globe before? And this represents a qubit. And you can do various things. And this company, by the way, these are pre-production. I told them I was coming here, and they shipped me some pre-production gear. That's just a demo to you guys. But I thought, rather than saying slideware, I thought maybe I couldn't bring a full quantum computer here. But I could bring these. So what you could do is, remember I said zero? The top is 0, one South Pole is 1. I don't know if you can all see this, but you flip it like this, and now it goes to the bottom. Yeah. And the other thing that you can do, you tap them together, and it does entanglement. Oh. And if I do something, if I do this, it turns it off. It destroys the entanglement. So this is a company that I just thought it would be interesting. I thought you guys would get a real kick out of this. There you can coyote again. And you can do those gates, moving around. You can do what are called qubit operations, those types of things. The company actually got started maybe 6 months ago. They're being funded by Kickstarter. They're taking pre-orders. I think the price for these is about $300 for the pair. And they will start shipping the production units in April of this year. But they are looking, they're starting to talk with high schools and other things, putting together education programs. They have a lot of collateral material that will go with that. And, there's a lot of efforts. I didn't go into all the efforts in terms of developing the quantum workforce, but there are a lot of efforts here. And that's one of the things the U.S. government is funding. So, with that, I just want to give you a quick summary that there's a lot of things being done. The hardware and software is all improving rapidly, more than I actually expected 10 years ago. There will be things that will start coming into production over the next 2 years. That's without error correction, what we call quantum error correction. And then in about 3, 4, 5 years from now, they'll put quantum error correction in there, and that will make the machine even more powerful and start getting up to those dots you have to right that I was showing you before. And, a lot of users, that IBM conference I was talking about a week ago, there was like 500 people in the room from all sorts of enterprises, Allstate Insurance and JP Morgan and ExxonMobil, all sorts of companies. And many of them have put together teams, small teams to figure out, hey, how can we use this in our business? So it's going to have a lot of potential. So with that, I want to thank you. Appreciate your attention. If you want to keep up to date with what's happening, that if you look at, we have a free report. It's free like the library is free. You can go to that website, quantumcomputerreport.com, and right on the homepage it says sign up here. We issue a newsletter every Sunday of all the things that have happened over the past week. And you can read all the news and then click on it to do the things. And then if you actually had something you want to do in quantum computing, if you're an investor or if you want to know more about applications or market sizes, our parent company, G2I, Global Quantum Intelligence, that's the one on the upper right. That's really what our business is. We provide service to the community for that. So thank you, and I appreciate the time.
Great. Thank you very much, Doug. I wanted to open it up for some questions. We have the coffee cookies outwards, but I know there are questions in the audience. So, and if you need to leave, then that's fine too. But let me start with in the back. And John, Doug's going to run back there with the microphone. Okay. We'll ask you guys to just stay settled here. We'll take questions.
True with that. It's like I said, Mom.
Hello. First of all, thank you for doing this presentation. 2 questions. First one, is it possible to get the slides?
Hi.
Let me just say this whole thing will be recorded in the website.
Oh, there is.
Flowery Foundation.
Yeah, there.
For free.
That's there.
Great. And second question is, you kind of mentioned that in the public markets, there's a bunch of speculative companies like IonQ and Orgetti and D-Wave that have, 25 billion, 30 billion market caps, and 10 million revenue. And then you have companies like IBM, Google, NVIDIA, they're large market caps, where quantum is just a small portion of the overall market cap. Just kind of curious, obviously not a financial advisor, but to the extent that if someone asks you, like, which public company you think is most intriguing in terms of like play quantum,
I knew that question would come up. Let me just make I'm going to make a general comment, which is, I actually think there's a lot of risk right now in investing in quantum. I think if you really want to invest in quantum, number one, I think you really want to have a 10-year time horizon. And number two, I think you might want to have invest in a market basket with stocks rather than just picking one. Maybe you want to pick several of them and spread the risk around. Here's where I see the risk. There's a lot of talk about AI bubble.
4 times spent.
And if that AI bubble collapses, I think it will take quantum down with it. Just from the stock market standpoint. The other thing to think about is, of course, the finances that I was talking about. You know, $25 billion market cap, you know, $10 million of revenue, in business school, they would say that doesn't make sense. The third is technology changes. Technology is very dynamic. It's sort of like, a marathon race where you may have leaders at the very beginning, and those leaders tire out. Somebody else comes in, And we see that in, like, the microprocessor market. Intel was the leader for many, many years, and what happened? Whatever reason, they didn't execute, or they focused on the wrong products, and now NVIDIA is the king. So I see that with all those different technologies in quantum, that we could very well happen. Right now, the superconducting technologies, companies like IBM, probably have the most use. That's because one of the reasons is it started earlier. And some of those others I talked about, like ion traps and neutral atoms, they started much, much later, but they might have the potential to catch up. So that's why I recommend a market basket rather than just a single company.
If you were a young person today who was interested in this, what advice would you give them about where to go to build expertise?
So it turns out that a lot of quantum is based on linear algebra. So, study the math. Randy asked me to take all the equations out of this presentation. But a lot of those things, for example, I could show you how entanglement works with equations, but really get solid at your linear algebra, and certainly understand, how to program computers. The language that is of choice right now is called Python. It's used by like physicists, whatever. That's used in a lot of computing things. But at the same time, I would mention that as these quantum companies are starting to get more commercialization and producing things, it used to be, again, 10 years ago when I started, most employees had PhDs in physics in these companies. But now they're looking for mechanical engineers, semiconductor engineers, layout engineers, production managers, of course, legal, finance. So you no longer need, you don't need a full company full of physicists. In fact, you don't want a company full of physicists to have a successful company. What we would recommend, and there's an organization called the QEBC, Quantum Economic Development Consortium, that Don and myself both belong to. We did a study. And, we saw this trend that I was just talking about, that it's broadening out. You don't even need a PhD anymore. But what we did recommend is that universities establish like an introduction to quantum technology class, maybe one or two classes. And what that will do is will allow the mechanical engineer, the semiconductor engineer, to talk to the physicists. The physicists, the theorists, they can sort of give you an idea of what they want, but in order to communicate that, you sort of have to understand what they're saying. But you don't need to go into great depth, and that's why this introductory course, we think, will be so valuable.
If I could just add to that, I do a lot of quantum science education in the local area in Orange County. So talk to me later, I'll tell you more. Great. Have one more question here.
No, thank you very much. Great slides. Appreciate it. So in the area of quantum resistant protocols, it sounded like you were alluding that there will be only one, that there's quite a number.
No, there's several of them, actually.
Yeah.
What happened is when this problem of RSA being in jeopardy was first realized, I think in 2017, 2018, NIST started a competition. And they said, send in your algorithms and we'll start taking a look at them. I started with 69. And they went through phase 1, phase 2, phase 3. They announced the candidates for phase 3. And I think, if I remember correctly, there's like 5 or 6 of them that they've approved. And of course, during this competition, all the computer scientists at the various universities did their best to try to break many of those 69 algorithms, and they were successful. But the ones that lasted were ones that people were not able to break. And by the way, there's still more analysis happening. So the reason they decided to have more than one is because, unfortunately, people have come up with these algorithms. You have all these PhDs and whoever working for 7 years trying to break them. They didn't, but they can't theoretically prove that it won't be broken in the future by quantum. So there is a little bit of nervousness there, and they want to have backups. So that's why they're approving multiple ones, and they're still working on it, by the way. And also, there's a different approach. So what I just described is a software-based approach to being quantum resistant. There is a quantum approach where you use a quantum network to send these entangled photons over a network, and that you can theoretically prove by the laws of quantum mechanics that if a hacker comes in and they try to tap the line, then it's going to break the whole thing, and you'll know about it, and the people trying to use it know about it. So there are some different approaches, and again, we can go into a lot of detail. Maybe I'll come back next year for something to talk about that.
So we have a pretty good idea of how classical computers can be programmed. What's the difference with a quantum computer?
Well, the languages are different, but in some respects, it still can be quite similar. There can be libraries. At the lowest level, if you're familiar with a classical computers, program, your if statements and your for, all those, they actually ultimately get translated into gates. NAND gates, NOR gates, OR gates, all those types of things. Quantum is very similar, is that quantums are programmed, but with just different types of gates. Like C-naught gate, Hadamard gate, X rotation gate, those types of things. And on that stack chart, there was a lot of what I call software development kits. A lot of companies specialize in doing that, where people try to program at as high a level as possible. And then it goes through a process called transpiling, where the software will take those high-level instructions and take it down to those low-level quantum gates. And that's, by the way, but that's a big area of research. One of the roadblocks is that programming quantum computing is still hard today. And one of the things that we're looking at it, people are looking at, is to use AI to help that. So you may have described a problem at a very high level. I want to create a process that converts nitrogen to ammonia, into NH4, and the AI figures out what the quantum program is. Now that's still, again, 5 or 10 years now, but there's a lot of work right now to make that at as high a level as possible.
Okay, one more.
The one over here.
Thank you. I was just wondering what application of it, quantum computing excites you the most.
I would say it's overall, in terms of the overall impact of quantum, it's on the thing I call computational chemistry. I think that the drug discovery, the materials design, new batteries, that type of thing, that is going to be the thing that over the next several decades, that's going to be the area where quantum will have the greatest impact on people's lives. And our market studies, again, that market model I have shows that, we show all the different, we have all the different applications, but that, we believe that will be the largest market revenue source of value for quantum of all the other ones.
Okay. I want to thank Doug one more time with a round of applause. I also want to say he's not leaving immediately, so you can assault him up here at the podium if you want. But I want to release all the rest of you to enjoy your holidays and come back and enjoy the rest of the library programs for next year and have a nice evening. Thank you very much.